Hello, and welcome back. This video is about rate laws and how to get the rate laws from the experiment. Remember, we can't just determine the rate law. We have to look at the experiments, compare the data, and calculate the rate law based on the data from the experiments. So what we're going to be looking at is different trials of the same experiment with like different concentrations and stuff like that, okay? So let's take a look at this first example. And I'm looking at Unit 5 review problems, number 41, just so that you have a reference point. This first problem, we see that we have only one reactant. So we have A is the reactant, is going to products, and there's only one of them. So this person conducted an experiment, and in the first trial, we see that they used the concentration of A in molarity. The concentration of A was 0.1, and the rate was 0.053. So they took the concentration from start to finish and divided it by the time, and that's how they got the initial rate. Then they increased the concentration to 0.2, so they doubled the concentration, and they see that the rate actually goes up by a factor of 4. And in the third case, they tripled the original concentration, and the original went up by a factor of, looks like 8 or 9. Okay. So we can do that roughly, and we can see that it's probably not a first order because it's not going up consistently, and it's not a zero order, so it's probably between 1 and 2. So let's go ahead and calculate it. The way we do it is by comparing two of the trials. So the first time, what we're going to do is we're going to look at these two, and then we're going to use this one as our check. So we always want the bigger number on top so that we can eliminate fractions. And we see that it's rate 2 over rate 1. So that's what we're going to be comparing. Now our rate law is always K times the concentration. And in this situation, we only have one reactant. So we're just going to put A here to the n power divided by K concentration A to the n power. Now this is what we're solving for. Because the question is, write the rate reaction equation, and in order to do that, we've got to calculate K and N so that we can apply it to any situation where we have A, and solve for K. So those are all the steps that we're going to be doing. So now what we're going to do is we're going to fill it in with the information that we have. We have 0.2 molarity divided by 0.1 molarity, because that's rate 2 and rate 1. My K's cancel because they're the same regardless of equation. The only time K is going to change is if a condition changes. But this is held at a constant temperature, so nothing has changed. And the concentration for 2, oops, I put it in the wrong spot. The initial rate, I always do that. I'm not sure why I do that. The initial rate is 0.210 and 0.053. And the concentration for 2 is 0.2 to the n power, and the concentration of 1 is 0.1 to the n power. So 0.210 divided by 0.053 is 4. It's 3.9 something, but we can round it to 4. And 0.2 divided by 0.1 is 2. So here we see 2 to the n equals 4. So what does n equal? Yeah, n equals 2. Okay, that's fairly easy to see. Now you can do it by plugging in numbers here. 2 to the first is 2, 2 to the second is 4. So you can do that, or you can do the log law. So we can say log of 4 equals n log 2. So n equals log 4 divided by log 2. Okay, so you can do that as well if you wanted to. However you want to do that. Later on we might have to use this because our numbers won't be so clean. So that is it if you have only one reactant and you're basing the rate law based on that. So now what we're going to do is we're going to put it back into the third one in order to calculate for K. So in the third one, we see again rate 3 equals Ka to the second, because we just calculated that n is 2. So we have 0.473 equals Ka is 0.3 squared. So 0.473 equals K. 0.3 times squared is 0.09. And so then our K is 5.2, about 5.26. Okay. Again, use your calculator. We'll use I'll get my calculator later. So then when we want to write this out, what we're going to do is write the overall rate law. So they asked for the overall rate law. And the overall rate law would be rate equals K, which we had as 5.26, times the concentration of A squared. Okay, so that's the overall rate law. So if we ever had any more data, we could just plug it into that to determine the rate. And this is how they do medicines and everything else, right? Because they want to make sure that the medicine is able to help you without killing you, right? Or not being effective. So we want to make sure that the rate is effective. All right? Okay, so now let's go on to number 2. Okay, so the second example problem is problem number 45 on that same review sheet. And in this case, they give us the reaction. So we have nitrogen dioxide plus fluorine gas yields fluoronitrite, or nitrogen dioxide. All right, so let's take a look at this. We want to find the rate law, and then we want to solve for K and N. So let's solve for N first, and then N and M, and then we'll solve for K. So here we see that these two are the same. So we can eliminate this reactance effect by taking these two trials. So in this trial, this one was held constant, and in the next trial, these two were held constant. So we're going to take 2 and 1, and then we're going to eliminate NO2 by looking at 3 and 2, and then we're going to plug both of them into this one to determine the K. So that's the plan of attack. Okay, so let's start out with 2 and 1. So we have rate 2 over rate 1 equals K. Again, K is going to be a constant, so we're going to get to rule that out. We have NO2 to the N, and then we have F2 to the M. Then we have NO2 to the N, and F2 to the M. Okay, my rate for 2 is 0.051. My rate for 1 is 0.026. K's cancel. My concentration for NO2 is 0.2 to the N. I can use parentheses now. That is the concentration. And concentration for F2 is 0.1 to the M. Concentration of the first one is 0.1 to the N and 0.1 to the M. Now we can see that these are the same too, so those can cancel out. So now what we're going to do is we're going to do the 0.051 divided by 0.026, and that's, again, very close to 2. And then 0.2 divided by 0.1 is 2 to the n. So we see that n equals 1. So if we were going to rewrite the rate law, we're saying rate, overall rate, equals, we're going to still solve for K, the concentration of NO2 to the first power, so we don't need to write to the first, and now we've got to calculate it for F2. So we're going to calculate it for F2 by doing the same thing, but we're going to look at rate 3 and 2. So rate 3 over rate 2, and we already know that K is going to be the same, so I'm not going to write K. And I already know that NO2 is going to be the same, so I'm not going to write NO2. I'm just going to write the F2. So the concentration of F2 in rate 3 is 0.2 to the M. And for rate 2, it's 0.1 to the M. And I know that the rate for 3 is 0.103, and rate for 2 is 0.051. So here we see 0.2 divided by 0.1 is 2 to the M equals 0.103 divided by 0.051 is also 2. So M also equals 1. So in our rate, we know that the overall rate, this is the overall law, we have NO2, the concentration of NO2, and we have the concentration of F2. So whatever these two are together, we multiply them together and multiply it to the equilibrium constant. Now, we got to solve for the equilibrium constant. And the way we do that is by plugging in both numbers into the rate for this. So we're going to use rate 4 to solve for K. So in rate 4, we have 0.411 equals K times the concentration of 0.4 times the concentration of 0.4. And remember, the exponents are 1, so we don't have to write them. And now I am going to have to use my calculator because I need to have it a little bit more accurate than I've been doing it. So we have 0.411, 2.569. So K equals 2.569 at constant temperature, at this temperature, right? So then we're going to take this K and plug it into this equation. So 2.569 is K. So I can discover the rate of any concentration of a reaction between NO2 and F2 by finding the concentration of each of these and multiplying it by the rate constant, and that will give me the overall rate of this. Now the last thing is doing units, all right? So the unit for NO2 is molarity, and the unit for F2 is molarity. The unit for rate is molarity per second. So what has to be the unit for my K value? The unit for my K value has to be divided by moles seconds, right? Because I want molars to cancel, and I want it to be molarity per second. So the unit for K, the unit for this K, is actually per molarity per second. So it'd be 2.569 capital M 1 to the minus 1, because it's going to be put in the denominator, seconds minus 1, because that's going to be put in the denominator as well. So that's something we look for as well. We look for the units. Now the last thing to look for is the overall order of reaction. The overall order reaction is 1 plus 1 is 2. So we'd say that the overall order of this reaction is 2. Alrighty, just keep replaying this until you understand it. It's pretty straightforward, but it does take a little bit of time to assimilate the process so that you know what you're doing going forward. So let's take a look at one more example problem. Okay, this last problem is on that review sheet, and it's problem number 46, and it involves, again, two reactants. So in this first reaction, we kept them equal, and we saw an initial rate. The second trial, we doubled this first one, and we did see a doubling of the rate. So we know that that's going to be a first order. And then in this next one, we doubled this one and kept this the same. So we wanted to see how this works, and this works a little bit less than a double. So that's going to be something we're going to have to calculate. And then we plug it into the last one, where it's 4 times as much as the original. So it should be 4 times as much as the initial rate. All right, so let's take a look at how to do this. Or if it was first order, it'd be 4 times, but it's a little bit more. So it's going to be a little different. The reaction rate is going to be a little different. So we're going to look at these two and make this constant, okay? So the rate for the experiment 2, trial 2, is 0.100, and no, the rate is 0.029, equals the concentration of the CH3Cl, which is 0.1 to the n, because we're calculating for n. K is going to be held constant, so we don't have to worry about K. And the first trial is going to be 0.014, and the concentration is 0.05 to the n. So 0.029 divided by 0.014 is 2, and 1.1 divided by 0.05 is 2 to the n, so we see that this is first order. Okay, so it's first order in relationship to CH3Cl, first order. So we have the concentration of CH3Cl is first order. Now let's take a look at the concentration of Cl2. For this, we're going to have to hold this one constant and look at these two. Okay, again, it's going to be the rate 3 over rate 2, because we want to have no fractions, divided by 0.0029 equals 0.1 to the m. Again, K is the same, so we don't have to write K. Now 0.1 divided by 0.5 is easy, right? It's 2, so it's 2 to the m. Then we have 0.041 divided by 0.029, and we come up with 1.41. So 2 to the first is 2. So this is less than 2, right? M is less than 2. The easiest way is to just do your log. 1.41 divided by log 2 equals m. That's the easiest way. But another way is to take this and try the square root of 2. Okay, because some of you guys are familiar with how this is. So the square root of 2 would be 2 to the 0.5. And guess what? It's 1.41. Okay, so we know that m equals 0.5 or 1/2. So when we're writing the rate according to Cl2, it would be 1/2. Okay, so it's the square root of the concentration of Cl2 on this one. Now the last step is to calculate K. So what we're going to do is we're going to plug it into this one. So we're going to have the rate equals the concentration of the CHCl to the first times the concentration of the Cl2 to the 1/2 times K. So we want to solve for K. So let's plug in the numbers. So the rate is 0.115 concentration of CHCl3 for rate for the trial, fourth trial, is 0.2 times 0.2 to the 1/2. Okay. So K equals 0.2 times 0.2 to the 0.5 and then I flip it to get it to the other side. 1.286. 1.286. Now the overall rate law then can be written, but we got to do this units first because these units are going to be a little bit gnarly, right? Okay. All right, so this K, this is molarity, and this is molarity to the 1/2. And this is molarity per second. So we need to know that K has to be per second, and it has to be per 1/2 because we need molarity per second. So we got to get rid of this molarity 1/2. So what we're going to do is we're going to throw it on the bottom. So we're going to put a negative 1/2. So our unit for K is going to be whatever the number is per second per molarity 1/2. So this unit for K is going to be, I'm going to write it the molarity first, molarity negative 1/2, second negative 1. Now if you guys want to put it in the denominator you can, but it's a little bit more confusing to do that. So I just write it as a negative because whatever I have to put on the bottom is going to be a negative for me. And again, I need these two to cancel. So I'm left with molarity per second. I need to be molarity per second. So the overall rate law would be the rate, okay, that one doesn't look that great. It's green. The rate of this reaction equals 1.286 per molarity 1/2 per second times the concentration. So we're doing the overall rate law, so I'm not going to plug anything in. Concentration times the concentration of Cl2 to the 1/2. Okay? So that's the overall rate law for this reaction. Now, what's the overall order of reaction? The order of reaction is it's first order in relation to chloromethane, and it's 1/2 order in relation to chlorine. So our overall order would be 1.5, or we would write it as 3/2. Okay, so our overall order would be 3/2, right? Because this is a full one and this is a half, so 1.5 is the same as 3/2. So my overall order is 3/2. Okay. All right, we're going to do a lot more practice, but hopefully this video will at least get you started and will help you understand how to work these problems should you be given one reactant or two reactants or even three. Woo! Let's see if we can graduate up to 3 reactants. All right, have a great day. See you in class.